In this video, we're going to go over different situations that you would use the formula for exponential growth and decay. So we're going to go over a couple of notes. We're going to introduce the formula. We're going to talk about key words to look for that will tell you that you need to use the formula. We're going to go over examples 1, 2, and 3 together. And then I'm going to leave examples 4 and 5 for you to do as practice. Okay, so before we get into it, it is important to remember how to change percent into decimals because we will be using and dealing with percents, and you can't put them into an equation as a percent. They need to be changed into a decimal first. So if you don't remember, you take the number. So if we want to convert 12% into a decimal, you take 12. And remember, a number has a decimal at the end, right? 12.0 technically is what this number is. What you're going to do is you're going to take that decimal point and move it 2 places to the left. Okay, so 12% is the same thing as 0.12 in decimal form. Okay, another way you can think of this as is dividing it by 100, right? If you wanted to go backwards, you could either move the decimal back over to the right, or you can just multiply the decimal by 100. Okay, so we're going to do the same thing for these other 2 problems. That means that 25% is really 0.25 in decimal form, right? 25 cents is 0.25 of a dollar. Okay, 2.5%. This one's a little bit trickier. 2.5. Well, if you moved that decimal over twice, it would be 1 space over here, which means we need to fill this in with 0 as a placeholder. Okay, so that looks like 0.025 is 2.5%. Okay, so now that we have that refreshed and taken care of, we're going to be looking at mathematical modeling with exponential growth and decay. Now, mathematical modeling is the method of simulating real-life situations with mathematical equations in order to predict their future behavior. Okay, so this can be useful in a lot of different scenarios. Our focus is specifically on growth and decay exponentially. So this is the formula right here. Okay, A of t equals, let's just highlight this, P, and then parentheses, 1 plus or minus r raised to the t power. And I'm going to explain every single part of this. Okay, so first, we just use A to represent, I don't know, just random growth or decay. They just use the letter A to name this function. Okay, P, the number that goes in front, kind of like regular exponential equations, the P is the initial value. Okay, so that is like the starting amount, what you start with before the exponential growth happens. Then it's going to be 1 plus or 1 minus the rate. R is the rate. You take percent and change it into decimal. Okay? And then T is the time, however many days, years, weeks, whatever. T represents the time. Okay? And keep in mind that you will use the plus sign if you're talking about growth, and you will use the minus sign if we're talking about decay. Now, what would you be looking for in a word problem that will tell you it's about growth? Well, you will see words such as increases. You might see compounded annually. Okay, that is used in terms of like investing money. Okay, you earn a certain amount compounded annually. That will be exponential growth. And you'll also see earns interest. So these are different phrases to look out for that will tell you to use the plus sign in our equation. Okay, so now decay, certain words, obviously decreases is going to tell you we're looking at decay. And something else you might see that you might not be familiar with is depreciates. Okay, that's like if something loses value over time, it's going to exponentially decay. All right, so those are our key terms. So now let's actually go through an example so that we know what all of this means and we can put it all together and see how this formula is used. So if you look at example 1, it says a painting is sold for $1,800 and its value increases by 11% each year after it is sold. Find the value of the painting in 30 years. So right away, I see a keyword. I see increases. Okay, that tells me I'm going to be using growth. Now, let's just copy our formula down real quick so that we have it. So our formula is A of T equals P times 1 plus or minus. Well, I know that we're going to use the plus because it's increasing. So 1 plus R raised to the T. Okay, so now we have to fill things into the formula. Well, P represented what? Go back to our notes. P represented the initial value. So for this problem, it tells us that the painting starts off at a value of $1,800. That's our initial value. So I'm going to start writing this down in the formula. We start with 1,800 for P. Now we're going to have our parentheses. We're going to have 1 plus, and then we have to fill in what R is. Well, they tell us that our rate is 11%. But I'm not just going to put 11. I need to change this into a decimal. So remember, 11 changed into a decimal, 11%. Move that decimal over twice. Okay, that is 0.11. That's our rate. So I'm going to put that in as well. And then the only thing missing is time for T. Well, they want us to find the value after 30 years. So 30 is going to go in there. Now the hard part's done. All you need to do is put exactly what you see here into your calculator. When you do that, you are going to get 41,206. And then since we're talking about money, right, the value of the painting, I'm going to round to 2 decimal places after the decimal, okay, to the 100th place. So this is $41,206.13. That's what the painting is worth after 30 years. So let's just do one more example just so we get the hang of how to use this formula, and then I'll have 2 practice examples for you guys to do on your own. Now, since I know this is an exponential problem, I'm just going to copy my formula before even reading it, just so I have it in front of me. That's a good idea to do. Okay, so this problem says the population of a town is decreasing. I'm going to highlight that. It's one of my keywords. Decreasing at a rate of 3% per year. In 2005, there was 1,600 people. Find the population in 2013. Okay, so they are kind of hinting at our time here. They tell us we're starting at 2005 and we're ending at 2013. So how many years is that? Well, 2013 minus 2005 gets us 8 years. So 8 is going to be our T. What's going to be our initial value? P. Well, the starting year was 2005. What was the population in 2005? They say that was 1,600. So that's going to be our starting value. Our rate, well, they say it's decreasing at a rate of 3%. So 3% is 0.03. 2.03 in decimal form. Right? And am I going to use the plus or the minus? Well, it says decreasing, so I'm going to use the minus. So what we have is 1600 parentheses 1 minus 0.03, and it was 8 years, so raised to the 8th power. Okay, so when you put this directly into your calculator, exactly how you see it, you're going to get 1,253.99. Well, we were really tempted to round this up because of the 0.99, but you can't really make a point something of a person, so we can't round this up because we're talking about population, we're talking about people right now, so we're going to actually have to round this down. So the population is going to be 1,253 people. Okay, after those 8 years passed. Okay, so I'm actually going to, for now, just leave it as these two examples, just because I don't want the video to get too long. So what I'm going to do is I'm going to ask you guys to do problems number 4 and 5 as practice, and that's it, okay? After you guys have a chance to do practice on this formula, we will go in a little bit more detail. I'll do the other examples on this sheet, but for right now, all I want you guys to do is just practice plugging into the formula. So problems number 4 and 5 should take care of that for you.